Now we want to look at identifying all of those same characteristics, but only by investigating the function and not looking at its graph. We can start off by finding all real zeros, which is simply the process of taking each of our individual factors, set equal to 0, which will give us x equals 6 and x equals negative 5 as all of our real zeros for this given function. Then we want to identify the multiplicities for each of those zeros. In this case, x minus 6 will have a multiplicity of 3, and x plus 5, since that factor is being squared, will have a multiplicity of 2. Again, what that's telling us is that at x equals 6, our function will cross the x-axis, again informing us about the behavior around that intercept. And at x equals 2, our graph will touch the x-axis, but then turn back away from it. We can identify the maximum number of turning points of this function by again considering what's happening to our function as we approach positive and negative infinity. Let's see, in this case we're actually considering g of x. So for those extreme values of x, our function is approaching x cubed times x squared. Where again, all I'm doing here is taking the x terms of each of these factors and then also multiplying by any constant factor that we might have. In this case, there's not one there, so x cubed times x squared will give us x to the 5th. So our polynomial is of degree 5, meaning our maximum number of turning points in this case would be n minus 1. So 5 minus 1, or 4. And then we're asked to describe the end behavior of this function, since we already know that the power function corresponding to our function for those extreme values of x is equal to x to the 5th. We know that our function at its extremes is going to be mimicking this behavior. So we can say that as x approaches infinity, our function g of x will be approaching infinity, and as x approaches negative infinity, g of x will be approaching negative infinity. We'll look at two more examples to reinforce this process of identifying the behavior of a function without looking at its graph. For example 3, again we want to find all real zeros, which means we'll take each of our factors, set equal to 0, and solve. In this case, x minus 8 equal to 0 will give us x equals 8. Taking x squared plus 25 equals 0 will give us x squared minus 25, which gives us no real solutions. So notice that what we've been asking for in each case are the real zeros for our function. What we'll investigate a little bit later in the semester is that this function does have some complex zeros, or zeros that involve complex or imaginary numbers. For now, though, we're only focused on real solutions. So x equals 8 will be our only real zero and our only x-intercept. Since x minus 8 is being raised to the 3rd power, that 0 has a multiplicity of 3, meaning we'll be crossing the x-axis. For extreme values of x, our function h of x will be approaching negative 5 times x squared times x cubed, or negative 5 x to the 5th. This means our maximum number of turning points would be equal to 4, which is 1 less than the degree of our polynomial. And that based off that power function, for extreme values of x, our function is going to be mirroring behavior like this. So we can say that as x approaches infinity, h of x is approaching negative infinity. And as x approaches negative infinity, h of x is approaching positive infinity. In example 4, we'll again take each factor, set equal to 0, which will give us x squared is equal to negative 8, and x squared is equal to negative 9. For now, since we're only considering real zeros, these two equations lead us to no solutions. So k of x has no real zeros, meaning it has no x-intercepts. So in this case, the graph of our polynomial function would never intersect with the x-axis. But later in the class, we'll come back to the idea of complex zeros, zeros of the form a plus or minus bi, if you've seen that before. If not, nothing to worry about for right now. For right now, what we'll say is there are no real zeros, which means part B is not applicable. Since our function has no zeros and has no x-intercepts, we can't learn anything about its behavior, at least from those two questions. We do know that for extreme values of x, our function is going to be approaching 3 times x squared times x squared squared, meaning our function is approaching 3x to the 6th power. Since, as a quick review, what we would do would be take our x squared raised to the 2nd power, we would multiply those two together to get x to the 4th, plus the 2 from the other x squared will give us x to the 6th power, meaning our maximum number of turning points would be 5. And since our function for extreme values is behaving like 3x to the 6th, we know we're going to have something looking like that parabola shape pointing up for our end behavior. So as x approaches infinity, k of x will be approaching infinity. And as x approaches negative infinity, k of x will still be approaching positive infinity.